Assalamualaikum warahmatullahi wabarakatuh. We from Faculty of Civil Engineering and Built Environment, Mechanic of Material, BFC20903. The topic that we discuss is material fatigue. Material fatigue is a type of damage or failure which is caused by fluctuating or cyclic stress. Under the effect of fluctuating stress, a point comes when the material is fractured. This level of stress is called fatigue stress and the failure called fatigue failure. These objects will experience moderate to severe cracking due to their differential forces. A collection of cracks on the object's surface can propagate structural failure of immediate remediation if efforts are not implemented. Structures fail when subjected to a cyclic load due to an experienced stress range below the static material strength.
The next slide that I will present is the background study of fatigue material. Firstly, in 1837, Wilhelm Albert published the first article on fatigue. He devised a test machine for conveyor chains used in the coastal mines. Next, in 1842, William John McCone Rankin recognized the importance of stress concentrations in his investigation of railroad axle failures. F. Braithwaite reports on common service fatigue failures and coins the term fatigue in 1854. In 1903, Sir James Alfred Ewing demonstrates the origin of fatigue failure in microscopic cracks. Later on 1940, Sidney M. Caldwell published first rigorous study of fatigue in rubber. In 1970, W. Elber elucidates the mechanisms and importance of crack closure in slowing the growth of a fatigue crack due to the wedging effect of plastic deformation left behind the tip of the crack. Finally, in 1986, comprehensive wear fatigue damage of active systems is first formulated, leading to the creation of turbo-fatigue.
Characteristic of fatigue in metal alloys, and for the simplifying case when there are no macroscopic or microscopic discontinuities, the process starts with dislocations movements at the microscopic level, which eventually form persistent slip bands that become the nucleus of short cracks. Macroscopic and microscopic discontinuities at the crystalline grain scale, as well as component design feature which cause stress concentrations, which is hole, keywise, sharps, change of load direction, are common locations at which the fatigue process begins. Fatigue is a process that has a degree of readiness, often showing considerable scatter even in seemingly identical samples in well-controlled environments. Fatigue is usually associated with tensile stresses, but fatigue cracks have been reported due to compressive loads. The greater the applied stress range, the shorter the life. Fatigue life scatter tends to increase for longer life. Damage is irreversible. Materials do not recover when rested. Fatigue life is influenced by a variety of factors such as temperature, surface finish, metallurgical, microstructure, presence of oxidizing or inert chemicals, residual stresses, scuffing contacts. Some material exhibit a theoretical fatigue limit below which continued loading does not lead to fatigue failure. High cycle fatigue strength can be described by stress-based parameter. A load control servo test rig is commonly used in this test, with frequencies of around 20 to 50 Hz. And lastly, low cycle fatigue is associated with localized plastic behavior in metal. Thus, a strain-based parameter should be used for fatigue life prediction in metals. Testing is conducted with constant strain amplitudes, typically at 0.01 to 5 Hz.
Assalamualaikum. My name is Aiman Hakimi, and I will talk about stage of fatigue. So, stage of fatigue happens when the material that have under repeated stress Having a maximum value less than the tensile strength, fatigue has been separated into regions of high cycle fatigue that requires more than 10 power of 4 cycles to failure where stress is low, and low cycle fatigue where there is significant plasticity. So there are three stage of material fatigue, which is the first stage is initiation, the second stage is propagation, and the third stage is final rupture. So the first one is cryination. Cryination is the most complex stage of fatigue fracture. The most noticeable factor due to the fatigue fracture is by irreversible change in the material such as metal that caused by repetitive shear stress. The accumulation of micro change over a large number of applications or called by cumulative damage. This cumulative damage become the main factor that cause cryination on the material. So this stage is it is said cannot be prevented. This step also can be bypassed entirely if the crack form at a pre-existing stress concentrator, such as from an inclusion in the material, or from a geometric stress concentrator caused by a sharp internal corner or fillet. At the beginning, the area that undergoing crack is very small. It never extending more than 2 to 5 rand around the beginning. After the material experience through the first stage, and propagation stage will happen automatically. The rate of crack growth is primarily driven by the range of cyclic loading, such as mean stress, environment, and short crack effect. So when the mean stress become higher, so the rate of fatigue crack growth also become higher. If the environment factor, the rate of growth become higher when the moisture is increased. Material like aluminium, the crack can generally grow from the surface where water vapor from atmosphere able to reach the crack and dissociate into atomic hydrogen. And the third factor, which is short crack effect. Short crack usually grow faster than expected. Factors for the crack effect is the stress, the three-axial stress state and the lack of crack closure associated with short crack. So the characteristic of short crack is the crack are smaller than 1 millimeter, and cracks are smaller than the material microstructure. So the which is final rupture. So when the stress exceed a critical value known as fracture toughness, unsustainable fast fracture will occur. The final rupture or final failure can be ductile depending on the material, thickness, temperature, and the applied stress. This stage will happen suddenly, and the fatigue fracture surface of broken component are typically smooth and show no evidence of plastic deformation.
Assalamualaikum. My name is Mohammad Shalihin bin Samsudin, and I will talk about theoretical studies on material fatigue. The SN curve test that show the relationship between stress and number of cycles to failure. Fatigue strength and fatigue life are two parameters used to describe fatigue behavior. This is a curve showing a fatigue limit. The fatigue limit is observed on the plot as a horizontal line as shown in the figure, which representing the largest value of stress that will not cause failure and becomes independent of the number of cycles. This is a curve that does not show a fatigue limit. The relationship for the latter curve show the number of cycles a metal can endure before failure for a range of applied stress level. Fatigue variable. The state at a point in the material can be described by many different variables such as stress, strain, or energy dissipation. A load cycle is defined as the duration from one peak in the studied variable to the next peak. This is illustrated by the figure beside, where stress is the fatigue controlling state variable. And this is the relation between the different fatigue stress variable.
Next, the slide that I will present is experiment on fatigue material. The first experiment is load control high cycle fatigue. A high cycle test tends to be associated with loads in the elastic regime. Testing the fatigue life of metals under load control is the best way to obtain the fatigue strength in the fatigue regime where strains are predominantly elastic throughout the test. High cycle fatigue HCF tests are often conducted on smooth bar specimens in load, force, or stress control. The goal of the test is to determine the number of cycles to fracture for each specimen. Strain control fatigue testing is often done to stimulate the expansion and contraction of a material as temperatures vary. The number 2 experiment on fatigue material is the strain control low cycle fatigue experiment. The test is run in strain control with the load as a dependent variable. Low cycle fatigue is characterized by high amplitude, low frequency plastic strains. Low cycle fatigue can be particularly useful in the industries that rely on materials in temperature varying and cyclic conditions, including aerospace, architecture, automotive, oil and gas, and power generation industries. The LCF results allows engineers to study materials in greater depth, understand mechanical and metallurgical phenomena.
Unfortunately, the absence of hydrogen would not eliminate the VHCF phenomenon in steels, which shows that hydrogen is just one of the many factors that influence the fatigue strength of steels in gigacycle regime. Among others are the defects, inclusions, pores, size, shape, type, distribution, density, position with respect to acting stresses. Defect type, for example, can influence the stress state in the surrounding matrix and its cohesion to it. Temperature, environment, and matrix microstructures are additional factors that have significant effect on fatigue process. Obviously, for different type of steel or materials in general, the control factors would be different.